This video is the first of a series of tutorials discussing the LX7720 radiation-hardened motor driver for space. Let's start with a short introduction to the LX7720's features. The LX7720 is a mixed-signal peripheral, which works with either a radiation-hardened FPGA, such as RTG4, or a radiation-hardened microcontroller, such as the SAM RH71. The two chips work together to build a complete closed-loop brushless DC motor controller or a stepper motor control system. The LX7720 includes 6 bi-level inputs or comparators for rotor position feedback from an encoder wheel or Hall sensors. The comparators convert and level shift the slow edges from the sensors. A resolver interface offers an alternative rotational feedback method, or it can be used with an LVDT instead for actuator position sensing. This video provides an overview of the motor driver half bridges and then explains the fundamentals of the MOSFET gate drivers. Here's a block diagram showing the structure of an LX7720 half-bridge driver in more detail. The LX7720 contains 4 identical half-bridge drivers, like the one shown in blue here, plus a single charge pump at the top. The charge pump generates the high-side gate drive supply for the upper MOSFETs. On the left, there are UD-in and LD-in control signals from the system controller. These control the high-side and low-side half-bridge MOSFET drivers independently. Because the control signals are independent, the SCP input optionally prevents the high-side and the low-side MOSFETs from both being turned on at the same time. This would allow potentially high shoot-through currents to pass through the half-bridge itself. SCP stands for Simultaneous Conduction Prevention. At the bottom, there is a current sense amplifier block, which feeds a sigma-delta modulator. The SNS out sigma-delta stream is processed by the FPGA or the microcontroller that's operating as a system controller. Current sensing will be discussed in a separate video. For now, we'll just point out that in this circuit, the current source by or sunk by the half-bridge is being measured. The current sense amplifier can be configured instead to measure either supply current or ground current. The OC fault output will alert an overcurrent condition detected by the current sense amplifier. Not shown here, the LX7720 can be configured to automatically turn off all the half-bridge drivers if any overcurrent condition is detected. Now let's go over the fundamentals of a half-bridge driver stage, leaving current sensing out of the picture for the moment for simplicity. The essentials of half-bridge driver is shown here. Again, the LX7720 parts are shown in the blue block. The half-bridge itself comprises 2 external end-channel enhancement mode MOSFETs, or NFETs for short. The VMPS rail is the motor pass supply, which can be up to 80 volts. The VGS rail is the externally supplied 10 volts to 18 volts gate drive supply. To turn on one of the half-bridge's MOSFETs, we need to apply VGS between the MOSFET's gate and its source. In the case of the lower NFET, the source is grounded. The lower drive, LD gate output, therefore just needs to swing between VGS and motor ground. For the upper NFET, the gate drive situation is more complicated. The upper NFET source is also the half-bridge's output, so it swings from ground when the lower NFET is on to VMPS when the upper NFET is on. So, not only does the upper NFET's gate drive have to float with respect to the half-bridge's output, but it also needs to end up higher than the VMPS when the upper NFET is fully on. Each driver, therefore, generates its own individual floating high-side supply, VFloat at the VFLT pin for the upper NFET's gate driver. The upper drive gate output, UD, swings between VFloat and the SW pin. SW is connected to the upper NFET source pin, which, as discussed earlier, is also the half-bridge stage's output. One way to understand V-float is to consider it as being a copy of the VGS supply, but which follows the upper NFET source pin instead of always being referred to ground. V-float is supplied two ways. Firstly, capacitor CV float charges up to VGS through the external diode whenever SW is grounded by the lower NFET being turned on. The 1 ohm series resistor limits the peak charging current into CV float, which is usually a low ESR ceramic chip. The external diode is also in parallel with an internal diode. Using external diode is optional, but it's recommended because it allows a higher peak charging current into CV float. Now let's consider what happens when the lower NFET is switched off and then the upper NFET is switched on. CV float starts off already charged up to VGS as just discussed. It maintains V float during the upper NFET's turn-on transition. When the upper NFET is fully on, the voltage on CV float is now above the VMPS motor supply rail. However, CV float is discharging and we need a way to maintain it. This is where the charge pump comes in. The charge pump is a free-running converter that generates a high-side supply called V-boost, which is VGS volts above the VMPS motor supply rail. V-boost is automatically switched on to V-float to restore the voltage on CV float when the other NFET is switched on. This means that the upper NFET can remain turned on indefinitely. Also, CV float is fully recharged and ready for the next switching cycle. That concludes this overview of how the motor driver half-bridges operate with dual NFETs. In the next video, we'll discuss implementing practical half-bridge driver stages using either standard gate voltage or low gate voltage NFETs.